Welcome to Pre-Calculus. Today we will find side lengths in special right triangles. We'll take a look at 5 examples. I'm taking a look at the first example. I see that I have a special right triangle that has a 45-degree angle for one of the acute angles, and then it's got a 90 there, so it's definitely a right triangle. My task is to find the missing side lengths, and I want to leave my answers as radicals in simplest form. Whenever I identify a triangle that's a right triangle with one of the acute angles as 45, what I can identify is that the other right angle has to be complementary to the 45 degrees. In other words, they have to add up to 90. I know that because all 3 angles have to add up to 180. So if I've got a 90, what's left is 90, and then half of 90 is 45. Once I see that this other angle is 45 degrees, I really can identify that I've got a special right triangle. We give this one the name the 45, 45, 90 right triangle. And the reason why it's special is because I can find its side lengths without using the Pythagorean theorem. So I'm going to set up this 45, 45, 90. Another way you can think of this is that it's half a square. And essentially, I have set proportions that each of these side lengths has to follow. So let's derive the side lengths here, and then we'll apply it here on our example number 1. So if I say that I have a side length of x, I don't know what it is, but I know that it's x. In a 45, 45, 90 right triangle, I know that the other leg has to also be x because this is an isosceles triangle. Those base angles are both 45. Now, if I use Pythagorean theorem to solve for the hypotenuse, remember we call the hypotenuse generally c, I could label one of these legs as a, the other as b, and use Pythagorean theorem to come up with, in general, in terms of x, what's the length of side c. So again, Pythagorean theorem says that the length of the one leg squared plus the length of the other leg squared equals the length of the hypotenuse squared. I'm trying to find an expression to represent the length of the hypotenuse, and then I'll substitute in x's for a and b. Now I want to solve that in terms of x for c. So I see on this left side, I've got x squared plus x squared. So that's equivalent to 2x squared. And that is equal to c squared. So to finalize for just side length c, I would take the square root. And on this left side, the x squared is going to exit the radical. Square root of x squared is just x. And what's left in the radical is the square root of 2. And that gives me essentially my relationship among the 3 sides of a 45, 45, 90 right triangle. If I know the side length of a leg, the other leg is the same thing. And then the hypotenuse is that value, which is represented by x, times the square root of 2. The idea behind the special right triangle is it saves time. So once I've got the result, I just want to apply it here. So I see I've got a leg that's a length of 6. That automatically means that the other leg is also 6. And that would correspond with this isosceles arrangement in the 45, 45, 90. And then if I can identify that 6 is x, the length of the hypotenuse is just going to be 6 substituted in for x times the square root of 2. And that's complete. So once we have the pattern in place, finding the side lengths is very quick. Our second example is another 45, 45, 90. So again, I can identify this one because I got a 90. One acute angle is 45. Therefore, the other acute angle must be 45. But here, instead of having one of the legs, I'm starting with the hypotenuse C. Now, if I think about my arrangement that we had from the definition we gave to the side lengths on a 45, 45, 90, recall that the two legs were the same. We called those x, and the length of the hypotenuse is x times the square root of 2. So in general terms, for me to go from a length that I know is the hypotenuse back to a leg length, I just need to divide by the square root of 2. We can see that if I took that hypotenuse x squared of 2 divided by square root of 2, that would cancel and give us just x, which would match what we're calling the two leg lengths. So here I do have a hypotenuse length of 6. So to get u and v, they're the same. I just need to take 6 and divide it by the square root of 2. You can recall from a previous lesson, this arrangement's not acceptable mathematically because I'm trying to divide 6 by an irrational number. And so I do need to rationalize the denominator. And you can remember our strategy for that was very simple. I want to multiply by the square root of 2 divided by the square root of 2. So it's like I'm multiplying by 1, but what this will do is cancel that square root in the denominator. So what I've got is going to be 6 times the square root of 2. And then square root of 2 times square root of 2 is just 2. And then 6 divided by 2 is going to reduce to 3. And we get the value 3 times the square root of 2. And that's the value for both u and v, because remember on the 45, 45, 90, those side lengths are the same. Go ahead and box those. So first two examples dealt with the 45, 45, 90 right triangle. Let's take a look at the other special right triangle, the 30, 60, 90 right triangle. So the diagram here tells me, again, just two of the angles. I see the 90 there with the square in the corner. I also see 60. If I see that one angle is 90, one is 60, if I subtract those from 180, 180 minus 90 is 90, 90 minus 60 is 30. That identifies for me a second special right triangle. We call this one the 30, 60, 90 right triangle. And again, it's given to us as a shortcut to find the side lengths quickly if I only know one of them. Now, where we start with a 30, 60, 90 right triangle is really the equilateral triangle. So recall with an equilateral triangle, all the angle measures were 60 degrees. Now, I'm going to split that equilateral triangle down the middle. And this is going to hit that lower side at a 90. And it's also going to bisect the 60-degree angle at the top of the equilateral. And so you can see where our 30, 60, 90 is really half of a equilateral triangle. Now, if I call this lower side X, so keep in mind that's the shorter leg. You can tell that it's the shorter leg because it will be in between the 60 and the 90. I can make a case at this point to find the length of the hypotenuse because it came from an equilateral triangle. This X is exactly half of the full length of the lower side of the equilateral, which I could represent as 2x. Well, if the lower full side of the equilateral is 2x, so is this left side. It's equilateral. And so what we've got is an initial relationship between the hypotenuse and the shorter leg. What's left for us to find is how we're going to define this length of the longer leg. So different from the 45, 45, 90, the three sides of the 30, 60, 90 will be different. There's not a pair of sides that has the same length. Now I can find this by, again, employing the Pythagorean theorem to find this missing longer leg expression. So the parts that I've got are the hypotenuse, which has to be C. I can call that shorter leg A or B. So we'll just call it A. So if I'm setting up Pythagorean theorem, A squared plus B squared equals C squared, I'm going to plug in what I've got for A is X. So X squared. And also C I've got is 2X. I'll square that. And then I want to solve for B. So I'm going to just leave B squared as is. So I need to make some simplifications here. I'm going to start off by subtracting X squared from the left and from the right. Now I need to square that out on the left. 2X squared is going to be equivalent to 4X squared. So if I'm taking 4X squared and subtracting 1X squared, the result there on the right is going to be 3X squared. On the left, I had a cancellation. All that's there now is B squared. And so to finalize solution for B in terms of X, I'll take the square root. And we get this expression for the length of the longer leg. It's equivalent to the square root. Well, let me pause there. The square root of X squared is just going to be X times the square root of 3. And so that gives me a way of defining the length of the longer leg in terms of the length of the shorter leg. So in a kind of strategic view of the 30, 60, 90 right triangle, this shorter leg is in a way my home base. It's just X. The other two, the hypotenuse, which is 2X, again, is defined based on the length of the shorter leg, as is the length of the longer leg. That's X times the square root of 3. So we got to kind of make a distinction here. It's different from the 45, 45, 90. Essentially, I will always want to get back to the value of the shorter leg because I can define the other two just by multiplying it by either 2 or square root of 3. Now, once I have that pattern, I'm really good to go in order to solve a question like number 6. I can identify that it has shorter leg of 9. And so for me to get from the shorter leg to the hypotenuse, which is here labeled X, all I have to do is multiply it by 2. So X here is going to be 2 times what was X, 9, or 18. Similarly, that length of the longer leg, which is labeled here Y, is really just the length of the shorter leg times the square root of 3. So the length of the shorter leg here is 9 times square root of 3, and that in itself is complete. I'll box it. Again, the special right triangles are here for us as shortcuts. They give us a way to calculate missing leg lengths, missing side lengths quickly. Our fourth example here has to do with two 45, 45, 90 right triangles. So notice it's been complicated by the fact that these triangles are sharing side lengths and they are different in terms of being a leg or a hypotenuse from triangle to triangle. So I see that on this example number 11, I've got a side length 7 for the upper 45, 45, 90. So I'm just going to start by identifying that as my hypotenuse. So remember, when I've got the hypotenuse of a 45, 45, 90 triangle, if I just give again a general example, the hypotenuse is the side length times the square root of 2. So to get from the hypotenuse to a leg, remember from our first examples, I want to take that, divide by square root of 2. So I'm going to find, and notice I'm not going to try to calculate directly my missing side length x first. I really want to first capture this intermediate side that they share. So for the upper right triangle here, it's a leg. So I'm going to find its length. It's going to be 7 divided by the square root of 2. Again, I need to rationalize the denominator by multiplying by square root of 2 over square root of 2. So for this intermediate side, it's not my final answer, 7 square root of 2 over 2. So I found now the lower leg of that upper 45, 45, 90. Now, I want to calculate for this lower 45, 45, 90 triangle. So again, I need to readjust my perspective. I'm now in this smaller 45, 45, 90 triangle. And again, what was the leg on the upper one is now my hypotenuse for this lower one. So just like we had done with the first one, to get over to the leg of this smaller one, I need to take 7 square root of 2 divided by 2 and divide it by the square root of 2. So we'll write that and divide it by the square root of 2. Now that's a complex fraction. And recall with something like this, what I could do is simply cancel this square root of 2. The technical step here would be to multiply by 1 over square root of 2. It would cancel that in the denominator. But really, if I multiply there, it's just going to lodge the square root of 2 in the denominator by the original 2. So this is going to become 7 square root of 2 over 2 times the square root of 2. And then I'll have a cancellation. And my x is going to be 7 over 2. So in this example, we did have to really do an intermediate calculation to move from the one triangle to the next. And notice that a leg in one triangle could be a hypotenuse in another, just depending on how they share those sides. Our last example is a pair of 30, 60, 90 triangles that are fused on one side. So this one, I have a given side length on the upper 30, 60, 90. And I'm trying to move down to the hypotenuse length of that lower 30, 60, 90. So again, I want to find the measurement of the piece that they share. So I'm putting all my attention on the upper. I'm ignoring this lower, larger 30, 60, 90. So on the upper one, the piece that I've got, if I compare it to my template, is the longer leg. I'm going to identify that 6 as the length of the longer leg of the upper 30, 60, 90. Again, on my diagram, which is a different orientation from the one that we've got here, the upper leg is going to be x times the square root of 3. The shorter leg is x, hypotenuse is 2x. So the part that I'm identifying that corresponds with this 6 is that x squared of 3. So I can't directly calculate the length of that shared piece because it would be equivalent to going from x squared of 3 to 2x. What I need to do is really go back to my home base, which is the shorter leg, and then from the shorter leg multiply by 2. So to get from longer leg to shorter leg, x squared of 3 to x, I need to divide 6 by the square root of 3. That requires me to rationalize the denominator, multiply by square root of 3 over square root of 3. So that's going to give me 6 times the square root of 3 over 3. 6 divided by 3 is going to give 2. So I get that this shorter leg is 2 times the square root of 3. So where we are now is right here. So now I want to calculate the length of the hypotenuse by multiplying that shorter leg, 2 square root of 3, by 2. So 2 square root of 3 times 2 is going to be 4 square root of 3. And at long last, that gives me this intermediate piece, 4 square root of 3. And at that point, I can change my focus now to this lower 30, 60, 90 triangle. So on it, this piece that was the hypotenuse of the upper one is now the shorter leg of the lower one. So we got to be used to kind of shifting what each piece represents for the triangle as we move from triangle to triangle. That's good news for us because remember the shorter leg is this x. So for me to go from x, 4 square root of 3, over to this side that's labeled with a variable on this triangle, that's my hypotenuse. I just need to multiply 4 square root of 3 by 2. In other words, I need to take the shorter leg length, double it to get the hypotenuse. So 4 square root of 3 times 2, 8 square root of 3, and that completes our search. The length of that hypotenuse of the lower 30, 60, 90 is 8 square root of 3. Thank you for joining for this investigation of special right triangles and using them to find missing side lengths. See you soon.